Okay, for what we will be looking into in continuing with Laplace transforms, okay, we're going to cross over to what are referred to as inverse Laplace transforms. And we have, by definition, okay, so you have a Laplace transform f of s, and you're taking the inverse Laplace transform of that. So we have the inverse Laplace transform of f of s is equal to the inverse Laplace transform of, whereupon we have f of s to be the Laplace transform of f of t. So we have the inverse of the Laplace transform of the Laplace transform of f of t to revert to f of t. Okay, and if you notice, we have in the table, just to sort of provide relative low-hanging fruit, if you have, say if you have a transform and you have the inverse Laplace transform of 1 over s, and if you notice we have from 1 over s, that corresponds to our function f of t, which is the constant 1. And also if you were to take, let's say for the inverse Laplace transform of 1 over s squared, and in this particular case, all right, so that reverts to t. And let's say that if you have the inverse Laplace transform, and we'll say that in this particular case, we'll say that we have the inverse Laplace transform of 3 over s squared plus 9. And if you notice, okay, we have 9 is going to be the square of 3. You don't necessarily have to write all of this, but just to sort of illustrate. So you have the constant at 3, and in the denominator, okay, 9 is going to be the square of 3. And if you notice, you have a constant over s squared plus the square of the constant. This is going to be in reference to what we have with the constant over the sum of the squares of s and the constant. And that is going to revert to the sign of the constant times t. So with the value of k at 3, okay, we have for the outcome, this will end up as the sign of 3t. And now, let's say that if you're looking at determining the Laplace transforms, and we'll say that we're not line up quite so directly with what we have been looking into so far. Let's say if you have, if you're looking at the inverse Laplace transform, and we'll say that we have of, let's say we have 5 over s minus 7. All right, so we have, so you have for s minus 7 in terms of that, which will line up. Looks like we have in the family 1 over s minus a. And for what is going to happen here, if you notice, okay, we have 5 in the numerator as opposed to 1. So we can extract, okay, the 5 and put out at the front. Okay, so you can have 5 times, okay, the inverse Laplace transform of 1 over s minus 7. Again, 5 is going to be a multiple. And for the reciprocal of s minus 7, you have a to be represented by 7. And this being reference to e to the at, where in this case we have 5 times e raised to the 7t. Right. And let's say that if you have something like the inverse Laplace transform, and we'll say we have 16 over s squared plus 49. And if you notice, you don't have quite a perfect match, okay, because you have 16 in the numerator. However, 49, which we have in the denominator, okay, that is going to be the square of 7. So to sort of line things up here, and sort of detaching the numerator from the denominator. Again, so 49, okay, is going to be the perfect square of 7, and just rewriting, okay, what we have here. Okay, so 16 over s squared plus 49, if I rewrite what I have in terms of 7, okay, so 16 over s squared plus 49, this would be 16/7 of 7 over s squared plus 49. So we have a multiple in this particular case. So you have 16/7 of the inverse Laplace transform of 7 all over s squared plus 49. And in this particular case, right, so you have with a constant over s squared plus k squared. So with the k value at 7, okay, we have the sine function will be the sine of 7t. So we have for this outcome, we have 16/7 of the sine of 7t. All right. Now, if we have, let's say we have the inverse Laplace transform, and we'll say that we have of 3s all over s squared plus 4. All right, so we have, in this particular case, right, so we have for 3s over s squared plus 4, you have s at the top, sum of squares at the bottom. So we're looking at arriving at the cosine function. Now we have a multiple with a 3. And we can extract that, say we have the inverse Laplace transform. And we have s over s squared plus 4. And again, so we have, with the value of k at 2, and we have with s over s squared plus 4, in this case s over s squared plus 2 squared, we have the cosine of 2t. So we have for the inverse Laplace transform of 3s over s squared plus 4, this will come out to 3 times the cosine of 2t. Now, if I have, let's say, the inverse Laplace transform, and we'll say we have 3 over s squared plus 25. Okay. Now, if you notice, okay, 25 is going to be the square of 5. So just expressing in terms of where the constant is going to be at 5. So again, just kind of spreading out, detaching the initial numerator from the denominator. Okay, so again, 25 is going to be the square of 5, and 3 is going to be 3/5 of 5. And so we're going to have 3/5, and the inverse Laplace transform of 5 over s squared plus 25. Okay, that is going to be the sine of 5t. Now, if we have, let's say, if we're looking for the inverse Laplace transform, and we'll now say that we have 2 all over s plus 10. Now, in the case of the inverse Laplace transform, okay, notice we have s plus 10, okay, and so you have a constant over, okay, a linear statement in s, and this will correspond to what we have for 1 over s minus a. Okay, so you have in this case, right, so 2 is going to be a multiple, and we have times the inverse Laplace transform. What's going to be 1 over, and we say we have s minus negative 10. And I'm rewriting this sum in terms of subtracting just to highlight, okay, what the value of a is going to wind up being. In this case, we're going to have at negative 10. So we have for the output will come out to 2 times e to the negative 10 times t. And let's say that if we're looking for the inverse Laplace transform, and we'll say that we have of 10 all over s to the 4th power. All right, so we have in terms of raised integer powers, this is going to be in the family of what we have in reference to t to the n. So we have n factorial all over s to the n plus 1. Okay, so we have s to the 4th. S to the 4th is going to be in reference to s to the 3 plus 1. And so your n value is going to be at 3. And 3 factorial is not equal to 10. So just kind of highlight, if I, again, detach 10 from s to the 4th, so I have the inverse Laplace transform. And one is going to be 10. And we're going to have over 3 factorial. And we have times, can you have 3 factorial? We have all over s. Now just do this color coding once more. You have s to the 3 plus 1. And I'll just take working across. Okay, so we have 10 over 3 factorial. Okay, and so 10 over 3 factorial, this will be at 10 over 6, which is reducible to 5/3. So we have in the crossover, so we have 5/3. And we have times the inverse Laplace transform. And we can just leave what we have here in terms of factorial notation. So you have 3 factorial over s to the 3 plus 1. Okay. And again, we have with the notation. Okay, so this being reference to t to the n. So with the n value at 3, it'll turn out that the inverse Laplace transform of 10 over s to the 4th, okay, that'll be t cubed. And we have for the final result, okay, this will end up at 5/3 of t cubed.